Hi. So today's presentation is about the question of how smooth the boundary of the planar convex hull of a graph of a Lévy path can be. Okay, this is based on our new paper co-authored with David Bank, who is my PhD student, and Jorge Gonzalez Cazares, who is my former PhD student and currently a postdoc at Warwick. Okay, so in our recent work, we characterized the Lévy processes that have smooth convex hulls. Okay, the boundary of convex hull is smooth, and so this might sound counterintuitive at first because it's expected and indeed true that convex hulls are piecewise linear objects. Okay? So in order to do this, in order to show that smoothness can actually occur, and one has to consider the set of slopes that these piecewise linear segments project down to. So a set of slopes is going to be some subset of real numbers, and what the key question is whether this set of slopes is locally finite or not. And in fact, what we show in our work is that the limit set of slopes, so the accumulation points of these random slopes, are actually deterministic. That set sits in the real line and is a deterministic set and can be characterized in terms of the characteristics of the underlying Lévy process. Okay? So there's a nice video Jorge made about this work. So in order to, and it's precisely these limit sets that sort of will occur at points like here, where interesting stuff happens and one wants to understand the growth rate of the derivative. You see, the limit sets are precisely the slopes, where after which immediately the process touches infinitely many times the convex minorant, say, which is this green function here. So at those points, I want to study today the growth rate of the derivative. That's one thing. Okay, let me just remind you briefly how this works and what the picture is. So what the lay of the land is, what the problem is that we're considering today is sort of Cits. So if I take a finite variation process, then there will be, for every such process, there will be exactly one such slope given by the natural drift. So in this picture, there's a convex minorant. You should imagine a graph of a path, which is not in this picture above it. And if this natural drift of this process is zero, then there will be an accumulation of sort of these line segments in zero, and the corresponding derivative will look something like this, you see. So what we want to do is we want to look at the point zero in this limit set, right limit set of slopes. So S is the set of slopes, which is random, but this limit set, even the right limit set, is deterministic, in this case just 1 point. In the case of finite variation, it's just 1 point. And we want to study how the derivative grows as time goes past this vertex time. So vertex time is very important. This is the first time we discover in our time interval, we discover the slope of size greater than zero. Okay, so another situation can happen in infinite variation is that we have this sort of accumulation on both sides, no problem. I mean, today I'm interested only sort of in growth in one direction because duality tells me how to deal with the other side. Okay, so I'm interested in sort of having things like modulus of continuity, and I can obtain that from the results that I'm going to describe today. Okay. Now, in the infinite variation situation, the picture is as follows. There are typically two classes of processes. There are the abrupt processes, which will have convex minorants of this type, where you see the derivative of the convex minorant always has a jump. Every time the process touches the convex minorant, it leaves it, and there's always a kink. There's a kink, so that it's sort of never accumulation points of touching, and so this means that this derivative is going to be discontinuous at the set of slopes, but the set of slopes is infinite, so it has to have an accumulation, and it has to have, if the process of variation has to have accumulation always at minus infinity times 0 and plus infinity at the end point at time of the interval. Okay, so today what I'm interested in is sort of how the derivative enters the real line, right? So how it grows as soon as it enters from minus infinity, okay, in this situation. Another class of process introduced in our previous work is the strongly eroded Lévy processes, where the phenomenon is such that sort of at every level, you see, at every level, this L plus of S is going to be equal to R. So for every slope, I see that, right? Every slope I pick, I look at the derivative at that level. The first time I look at the vertex time at slope S1, that's real time, and I look at the derivative immediately after, and the process sort of touches the convex minorant infinitely many times. And then the question of how it grows is relevant. So it's a non-decreasing function. You can have lower bounds, upper bounds. Okay, so it's sort of interesting behavior. And this can happen at any slope I pick. So slope S1, S2, S3. These are the questions that I want to answer. Okay. Now, let me give you, this was just sort of intuitive background. So what are the problems? Okay, let me just recap that quickly. So I have finite slope. Okay, I always take S in this accumulation point set of slopes. Okay, and then I look at how the derivative grows after the vertex time. Okay, so what does that mean? I'm interested in upper and lower functions of this derivative. I look at the increment of the derivative. Okay, immediately after, and I compare it to some deterministic function. I want to know whether I get a lim sup finite or infinite, lim infinite or infinite, etc. This is the sort of picture this corresponds to, right? So this is the sort of everything is shifted to zero. I look at the process sort of started at this vertex time, which is tau naught in this case, and zero is in this L plus of S. Right? So S, and I want to understand how the growth happens. And so understanding that will give me some new information also about Lévy meanders, which I will describe later. Okay, understanding this. And the second thing that I'm interested in is, of course, as I was saying, infinite slope, which happens for all infinite variation Lévy processes. Right at time zero, the slope is in fact equivalent to process infinite variation if and only if the derivative sort of converges to minus infinity at zero. And in that case, I want to know how this derivative enters, right? So again, I multiply it with some function f that goes to zero at zero, typically regularly varying function with positive exponent, and I want to then understand so when this lim sups are finite and infinite, and there's going to be some interesting sort of diagonal relationship between these two things, which is slightly unexpected. Okay, so let me get on with the results, right? So first case is I want to consider finite slope case with lower functions. Okay, I want to lower functions, finite slope case. I want to give a sort of comprehensive picture, right? So I want to make some assumptions and then tell you what actually happens. So these are the assumptions in this case. The details are not important at the moment. The thing to note is that it's test function mixed with marginal transitions of the process X. And the type of result that I get is I look at the slope in the limited set of slopes. I take a function f, which satisfies some technical assumptions, which are definitely satisfied if f is, say, regularly varying at zero with positive exponent. And then, if these assumptions 1 to 3 are satisfied, I can tell you that the lim inf is infinite. So what does that mean? It means that in that case, this guy grows faster than this function f with which test function which we are comparing. Okay? So if one fails, if this guy fails, then I can prove that this lim inf is zero. Okay? And I want to show that these assumptions are sort of close to necessary also. They're general assumptions, they're close to necessary. So if this lim inf is not zero, then one has to hold for some c. Okay? So what are these assumptions? I don't want to go into too much detail. One thing to note is this first assumption is to do with large jumps. It maybe doesn't look like that exactly, but it's to do with large jumps of this vertex time process. Okay, so these large jumps need to be controlled. And then there's a Borel-Cantelli argument in the background of this type of results. And so this assumption sort of tells me that some means converge to zero, and this assumption tells me that some variances will be bound. Okay? So this is still, in principle, hard to check, and what we do is we, in the paper, which will be on the archive very soon, we explain how to reinterpret them in terms of the characteristics of the process, in terms of, in this case, Blumenthal-Gatur index and related quantities. Okay, so in order to just make the presentation simpler, in the special case of alpha stable, these assumptions really boil down to the finiteness of this integral. You see, these assumptions were sort of mixing f and the law, but here they're just mixing f and alpha for alpha stable process, right? So if this integral is finite, I get that this is infinite. Otherwise, if it's infinite, then I get that this limit is finite. Right? A thing to note is that if I look at the situation like this, alpha stable situation, then this guy cannot have a limit which is neither infinite or finite, because the characterization is in terms of the finiteness of the deterministic quantity. So I find it very infinite. So this means that this, in this alpha stable case, I'm sharp, right? The assumptions are sharp. Also, another thing to note is that here alpha is assumed to be between 0 and 1. If alpha is greater than 1, then there are no finite slopes to consider, you see, because in that case there's too much activity and the process is abrupt. Okay? So this theorem sort of covers everything. Fine. Now, moving on to the upper functions in the finite slope case, I need to make stronger structural assumptions on the process. Okay, so they're in terms of but still broad, right? So they're in terms of the domain of attraction at 0. Okay, so I take alpha smaller than 1 and I assume that x is the domain of attraction of an alpha stable process at 0. So I normalize it with some g. This g is going to be slowly varying function times t to the 1 over alpha, and I assume that there's this limit, and the limiting process has a positivity parameter, and gamma 0, of course, I need to center, right? I need to center to get this kind of loop. And then, in this case, we give a theorem of this type, where we actually identify the class of test functions that sort of gives me the correct polynomial order, and sort of shifts the problem to the logarithmic order, right? So the difference in the behavior really is to do with this p, you see here. This p, and this p is just the power of the logarithm in here. Right? It's just the power of the logarithm. Okay, well, this g is t over g of t, where g of t is the normalizing function, So that tells me that this is not the best possible result, but it is certainly a result that shows you that in the case, for example, if I'm in the normal domain of attraction, so in other words, slowly varying function is just t times 1 over alpha, then what? Then I get the correct, as I was saying, the correct form of the exponent, but the logarithmic factor starts depending on the positivity parameter. You see, I would like to stress that, because the positivity parameter is a very complicated function of the fine structure of the jumps of x. Okay, so that's something that arises in the limit, and this is a quantity that I've not seen appear in lim sup type results, or lim-inf type results, or logarithm type results for the path or the supremum of the path. Usually what you see is only dependence on alpha, where the behavior changes. But here, already in the logarithmic level of the logarithmic rate, the behavior depends on this row. Okay. Right. Now, looking at the upper functions, the situations in the infinite slope regime, upper functions behave similarly as lower functions for the finite slope regime, as I said in the beginning. I don't want to go through too much details. The assumptions are sort of analogous, okay, you see, and the results that you get are also analogous, the general assumptions, and these assumptions can again be sort of reworked in terms of the characteristics. Of course, the theorem is slightly weakened because you have to make some assumptions, but in particular, if I make a lot of assumptions and assume x is alpha stable, then I get, again, a characterization in terms of some finiteness and infiniteness of some deterministic integral, right? So remember, f of t is t over ft here, you see. Where is this capital F of t here? T over ft, right? Okay. So that's the situation. Now, the lower functions are connected to the upper infinite slope regime, or behave similarly to the upper functions in the finite slope regime. And this is sort of interesting. You see, this diagonal connection is interesting because the lower function infinite slope regime deal with infinite variation processes, while the lower functions in the finite slope regime deal with finite variations processes, typically, right? But the structure of the proof, the structure of the theorem is similar, and again, this dependence on the positivity parameter comes I will say more about that in the last slide, a little bit more. Okay, so you can do the same sort of function, you can do the same analysis in the normal domain of attraction. But okay, so let me say just briefly how once I can deal with finite slope regime and I assume that 0 is this sort of limiting slope, this gives me something about the meander, right? So you see, if I have this result for this, I can characterize this what I showed you, right? Then I can integrate the denominator and numerator. It's like a L'Hopital, right? I will get the same sort of behavior for the limit for the convex minorant. Now the convex minorant is below the post-minimum process, which is essentially the meander, so I get this kind of result. And here you see the situation is slightly different. Here I've got lim sup assumption, so if I integrate I get a lim sup for the convex minorant, right? So this means that f of t dominates the convex minorant because the lim sup is 0 for sufficiently small t, but at the contact points, which are infinitely many, in this case with the path, I will get this sort of state. Okay. And I can, of course, characterize that using the results above. I don't want to go into too much detail, but here is the result that does that. Okay. Now, of course, one can also try to translate this into the sort of results about the path at time 0 in the infinite slope regime, and one obtains some stuff. But of course, this has been studied extensively over past decades, many decades. Okay, results like this are sort of dripping in. I've been of great interest, actually. So, but the point that I want to make here is that those results cannot be used directly to understand the behavior of the minorant in any sort of comprehensive way. You can do this sort of the negation of the statement, and you will get some statement about the lim sup, but you certainly don't get the full picture, right? And unlike sort of the result themselves here, or even if there's a supremum here, which sort of depends only on the behavior of the process on the small time interval as you're shrinking the time interval. This guy is sort of a global quantity because it depends. This is a convex minor. It depends on the path on the entire interval. Okay, on the entire interval, and so of course it's not so surprising that you cannot obtain stuff not about the convex minor, but about the derivative of the convex minor. This is the point. So how do we do all this? Well, what's in the background is the fact that the vertex time process is an additive process with strictly increasing paths. So infinite activity jump, additive process with strictly increasing paths. So we need to develop a theory for that. So studying growth rate of such processes. And so if such process started at 0 with this sort of Lévy measure in time and x, then you get this kind of relationship that characterizes the marginals, and indeed the entire law if you have it for all t. And then what is the process of interest is the right continuous inverse of y, right? This L of t is right continuous inverse. So in the context, for example, of local time, classical local time, you know that the inverse is the inverse of a subordinate. Here, this LT sort of serves as a function. We can apply it in our context. You see, so the question is what additive process do we need to use? So in the finite slope regime, we just look at the increment of the vertex time process, and then the local time, well, not the local time, but the inverse of that additive process is gives me this. My increment of the derivative, and in the infinite slope regime, there is, I need to do a time change. I need to go back to minus infinity, and then this guy is given by minus 1 over LT. And you see, this is where, this is really the basis for this diagonal connection that appears in this work, because this LT features in the opposite way. So lower functions for one or upper functions for the other. 1 over t connection. Okay, thank you. So this is the paper that will contain all this stuff. This is the paper that is sort of characterized as smoothness. I wanted to say at the end, so there's lots of things to study in this direction. Okay, there's many interesting open problems. Our results in this paper are not optimal. Their main aim is to present an overall picture and structure. Okay, but there's definitely room for improvement. And I hope you find that interesting and stimulating. Thank you very much.